Jai Hind everyone. Myself Suvarna Mujumdar, Assistant Professor in Electronics and Communication Department of Ajay Kumar Garg Engineering College, welcomes you on the lecture on Design a Combinational Circuit. The combinational circuit is a type of digital circuit in which the input and output is related in such a way that output of the circuit depends only on the present input. We don't require any memory element while designing any combinational circuit. In any combinational circuit, we have only basic gates. Either we design it using basic gates or we design it using a universal gates that are NAND gate or NOR gate. While designing any combinational circuit, initially we have to follow some steps, and the example of combinational circuits are like adder, subtractor, multiplier, comparator. Any circuit, any digital circuits which does not consist of any memory element, that is flip-flop or latch, we consider that as a combinational circuit. Now, in this particular lecture, I am going to cover about the how we are going to design any combinational circuit if a statement is or a problem is given to us, or if we have to identify the problem. So, the step by step procedure has to be we can consider in this way, and we have consider one example as a problem definition, and then I am going to implement that problem and we will draw a efficient circuit for that particular problem. Now, in this case also we have to we are going to discuss how we will find the components, whether we are going to go with universal gates or we have to design using basic gates. So, the first step is we have to define the problem. Now, in this particular example, I am considering the case where I am defining it as we have to design a combinational circuit which produce a 2's complement of a 4-bit binary number. So, we have to design a combinational circuit. The output is the 2's complement and the input will be a 4-bit binary number. So, first, as I defined the problem, I have to clearly I desired functionality. That desired functionality is the circuit has to work as a 2's complement circuit, and the input for these is a 4-bit binary number, and obviously the output will be a 4-bit number, but it is the 2's complement of a given number. Now, the second step for this will be we have to draw a truth table. What does this truth table consist of? This truth table may be consist of input and output, or we can say the truth table is nothing but it may map all the possible input combination with the desired output. So, we have to create a truth table as per our requirement. The requirement is the input is of 4-bit. And for each input combination, we must have a 2's complement output. Now, when we say that we have 4-bit input, I can like it, we have 4-bit input. So, the output will be, or we can say we have 16 combinations. From 4-bit, we will have a 16 combinations, that is starting from 0 to 15. Now, I have to create the truth table. So, we have input. We have to name these inputs. So, 4 variables we need. So, I can name it as W, X, Y, Z. And correspondingly, we have the output. Now, here I can name output as A, B, C, D. Okay. So, 4 input W, X, Y, Z. We have 16 combinations starting with 0, 0, 0. I will write all the 16 combination correspondingly. 0, 0, 1, 0, 0, 0, 1, 1. Now 0. 1 second, I can. W, X, Y and Z. And we have output A, B, C and D. So I have combination 0, 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and lastly 15. Now for each combination we have to find the 2's complement. So as we know, to find the 2's complement we have to first find the 1's complement and add 1 to that number. So from here if I go with 4 times 0, the 1's complement will be like this. Okay, when I add 1 to it, it will make it as 0, 0, 0, 0. Yeah. Now for case of 1, again I make it 1's complement and I add 1 to it, so it will become 4 1's. Now here in this case it will be 1, 1, 0, 1, but when I add 1 to it, it will become 0 and I make it 1. Okay. So in this way we have to first create the truth table for all these combinations. Okay. So for if I go with 3, then it will be 1, 1, 0, 0 and I add 1, so it will be like this. So it's 1, 0, 1, 1. But when I add 1 to it, it's 0, 0 and it will become 1 here. Now 1, 0, 1, 0 and 1. 1, 0, 0, 1. Now make it 0 and 1 added here. So it's 1, 0, 0, 1, 0, 1, 1, 1, but I add 1 to it, so it's 0, 1, 1, 0 and 1. It's 0, 1, 0, 1 and now it becomes 0 and this will become 1. Here it is 0, 1, 0, 0, but when I add 1 to it like this, 0, 0, 1, 1, but when I add 0 it will like this, 0, 0 and then we will have 1, 1 and lastly 0, 0, 0, 1. Okay. Now when we have do this table, now from this truth table I have to find as we know there are 4 output A, B, C, D. These are the 4 output of my combinational circuit. A is one output, B is another output, C is another output and D is another. So for each output I have to find a Boolean expression and then only I have to draw the logic diagram. So for A I have to find the terms or we can say min terms so that I can solve K-map or tabulation method and from K-map or tabulation method I can find a Boolean expression for A as an output, for B in terms of W, X, Y, Z. So from this truth table if I number it as min terms, so these are 0, 1, 2, 3 like these are the min terms my 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. For column wise I will check that for A what are the min terms available. Okay. So for in case of A I can find that the min terms for which the A output is high. So it's from 1 to 8. You can see clearly it's from 1, 2, 3, 4, 5, 6, 7, 8. So from min terms 1 to 3, 4, 5, 6, 7, 8. Now for in case of B, if I have to write, it is 1, 2, 3, 4, and then it is 11, 12, 13. So for B it is 1, 2, 3, 4, 11, 12, no sorry, not 11, it's 9, 10, 11, 12. It's 9, 10, 11 and 12. Now in case of C, it's 1, 2, 5, 6 and 9, 10. Okay. And I think 14. So in case of A, it's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7 and 10. We will have 10 also in this case. And in case of B, it is 1, 2, 3, 4, 9, 10, 12. And in case of C, like this. So we have to find the sum of product form, or we can decide it for product of sum form. If we go with sum of product, we have to find the min terms for which our output is high. And in case of product of sum form, if we have to draw it through NAND gate, then in that case I have to make a group of min terms, or we can say max terms, for which my output is low, 0. Okay, so for that I have to draw the K map, and we have to find the Karnaugh map for the solution for simplification. So I can just Karnaugh for A, B, C, D. And this I have to solve in terms of W, X, Y and Z. W, X and Y and Z are my input, and for these input I have to solve the K map for A. That is my first output. So in case of A, I found that my output is high for 1, 2 and 3, 4, 5, 6, 7 and 10. For these cases, my output is high. Now, this is 0 cell, 1 cell, 2 cell, 3 cell, 4, 5, 7, 6. In K map, 4 variable K map, this is 10. Not 10, it's 7, 8, 9, 10, 11. Okay, so for 8, I have this thing. It's 9, 10 and 11. Now, to solve this, you have to make a pair or quad, and if I change this color, you can find this. We have one quad like this, another quad, and to cover this one again we have one quad. So we have 3 quad and 1 single cell. Okay, so for this cell, if I have to write, it is WX bar, WX, W bar X, W bar X bar. This is Y bar Z bar, Y bar Z, Y Z, Y Z bar. So for this case, I will write W X bar, Y bar, Z bar for this cell. Then this pair, this quad, rest W, Y and Z are changing, only W bar X. Now for this quad, W bar is common and Z. So W bar and Z. And for last column, this one, for this quad, again we have W bar and Y. So in this way, we find A. Similarly, for B case, Okay, again for B, we will find it for W, X, Y and Z. Now in this B, I will take another color. I can take blue. So we can place 1. So here it's 1, 2, 3. Then 4, 5, 6, 7. Then we have 9, 10, 11. And we have this way. Okay. So from this, if we make a pair, this will be one quad. So for B, we have to write here it's y bar, z bar, y bar, z, y, z, y, z bar, w bar, x bar, w bar, x, w, x, w, x bar. So for this case, x bar is not changing and z is there. Now the second quad, for this case, again x bar is not changing and y is not changing. Now for this case it will be a pair. So here we can have x, y bar, z bar. Now similarly we will solve for C and similarly we will solve for D and we will have an expression for C. It will be C bar D plus C D bar, and case of sorry, not C, it's I will erase it, not both will not be the same. It will be y bar z plus y z bar, and in case of D it will be z. Okay, with the inverted one, W, then we have X, then we will have Y, and then we will have Z. Okay, W, X, Y, Z, and we have 4 outputs A, B, C, D. So in case of D, we have Z, so I can make it as D. In case of C, we have 2 AND operation and 1 OR operation. If I am going to design this using basic gates, then in case of C, I will have Y bar, Z and Y, Z bar, like this. Now in case of B, I have 3 terms, so I will take 3 AND gates and 1 OR gate. So 3 AND gates we have X, D bar, we have X, D bar, then we have X bar, C, and we have X, C bar, X, Y bar and D bar. Similarly, we will draw for A and we will have this logic diagram. So in this way, for any combinational circuit, whenever a problem statement is given to you, you have to first identify input and output from that problem statement. Then you have to draw the truth table. From truth table, you have to solve a K-map for number of outputs available. Like in our case, we have 4 outputs, so we solve 4 K-maps. And from 4 K-maps, we will find 4 different Boolean expression for each output. And then we will draw the logic diagram. So this is how you can design any combinational circuit whenever a statement is given to you. Thank you.